Thank you very much for inviting me to speak here. It's a great pleasure. We collaborated with Arthur on one long project, I think, for about 3 years, and this was, I think, the most fruitful time for me in mathematics. And in addition to that, I learned from Arthur what a log scheme is and what Betti homology of a log scheme. And in fact, the work I'm going to talk about is, grew up also from a question that we discussed a while ago with Arthur. And so the question is the following. So I have for log schemes and then I have various homology theories. Well, for example, I can look at the Tal homology. Or Betti, or say de Rham. Okay, and so if my log scheme happens to be defined over a finite field, so then this Tal-Eladig homology of X with QL coefficients, well, it's a vector space which is equipped with an action of the Frobenius. And one can Kummer-Tal, right? And one can check that for a reasonable scheme X, the eigenvalues are all Weyl numbers. Of course, they are of different weight. But in particular, because they are Weyl numbers, this gives me the weight filtration. And so the question is, so let's see whether I know how to use it. So, okay. So, can one define this filtration geometrically? Well, so I want a definition which would make sense for all these three theories. More precise, so you can ask for rational Betti homology, or you can ask even whether it's well-defined integrally, as for usual singular homology of algebraic varieties. So one can ask whether can one associate a motive. Vodsky motive. Motive to this X. Or maybe even a finer question, Motivic homotopy type. Well, I want to tell you so a little bit about this question. So what kind of homotopy type you expect to have? So and this, the answer lies in the construction due to Kate and Nakayama. So, okay, so I will recall it here. Nakayama construction. So they defined Betti homology. Okay. So that's Betti homology of a log scheme X. Say with Z coefficients, any coefficients. Well, to be by definition homology of a certain topological space. So this is just usual, so this is X log. So That's what Arthur explained to me. So this is just a topological space. Well, in many cases, it's a sorry. This my X is now over complex numbers, of course. Right. Thank you. So X is a log scheme over the complex numbers, and so this X, well, it's just in general. Well, it's a topological spaces, but well, in many cases, it's a manifold with boundary. It has some additional structure. So what is it? So this is a topological space which is equipped with a map, it's proper map, to X. So the construction is the following. So, well, I have my log scheme. So I will denote by X underline the underlying scheme, and M is the sheaf of monoids. So I have the sheaf of monoids. I have O star that sits inside it, and I have a map to O. Okay. So well, the only thing I care about, and in fact, well, it's true for the entire talk, is the group completion, M group. So this is a sheaf of abelian groups. It has O star sitting in it, and it has quotient, which well, I will assume I will look at fine log scheme, so it's going to be a constructible sheaf for a tile topology, or if you wish, you can consider a version of it for the risky topology. In fact, in my talk, it will be more convenient to consider all these as sheaves for the risky topology, because at the end, the object that, well, yeah. So let's stick to this. So this is you can think of this. Well, a good example of such lambda is just the constant shift supported on a divisor, for example. So you have such an exact sequence. And okay, so to a scheme and to such an extension, I want to associate a topological space. So how I want to do this? Well, if I have a point, well, I can sort of restrict my, so there is here a evaluation map, point X. And so from this extension, I can derive an extension of the stalk of this sheaf lambda at point X, and this will be M by C star. Okay. So this is just a finitely generated abelian group, and this is C star. So it's extension. Okay, so now.
But M sub X doesn't mean the stalk of M.
Yeah, it doesn't mean the stalk. It means push out. So, and here I have map from C star to S1, which is called the argument. So, well, let's give a name to this map. Let's call it gamma. So I look at all possible sections like this. We'll call it sigma x. So satisfying the property that if I compose gamma with sigma, I get argument. And so x look. Yeah.
Which is the same as sections of this splitting of this extension.
Mm-hmm. Well, push out of this extension, rather, right? So, and then this space as a set is just a set of all pairs x and sigma x.
Your lambda is torsion free because you assume Fs.
It need not be torsion free. I'm going to assume in a second. I will assume that it's Fs, but for the moment I don't even need this.
Really?
Well, so okay. So I consider all such splittings. Of course, there is a map to X, and I want to. And the fibers are fiber over point X is a torsor over home from lambda x to S1. So in the case of nice log scheme, Fs log scheme, this is just a real torus. Okay, and so then there is a topology on so any section of M group defines a function on X log with values in S1, namely it takes point X sigma to sigma of X applied to M. And I want these functions to be continuous. So I consider the weakest topology such that the pullback of any continuous functions on X is continuous, as well as these functions are continuous. Okay, so and that's a topological space, and I want to see whether I want to the ultimate goal would be to realize this the homotopy type. To leave this homotopy type of this log space into a Motivic homotopy category. So, so that the possibility of such construction was suggested to me by a long time ago by Maxim and also by Nori, somehow independent at the same time. So they explained to me one single example, which is kind of really the key example. So I want to tell you about this example. Okay. So what is so this the log structure, the log space that comes from as a special fiber of a semi-stable degeneration. So it will be this will be x0, this will be xt, and so semi-stable degeneration so it's strict, and moreover, so I will assume that there are no like triple intersections. Very simple. On my picture there will be only two divisors. Can be generalized in the case of many. So I have these divisors. This is D1, 2, and so then I have two line bundles on x0. Namely, I have L I, which is O of di restricted to x0. So this is so I have I is 1, 2, and so this Li comes with trivialization. If I restrict it, here is another piece of notation. Ui is the complement, x0 minus di. And Li is when restricted to Ui is canonically trivial. right? So these two structures, the two line bundles together with such trivialization can be organized as given such two line bundles is the same thing as given extension of z d1 plus z d2 by O star. This is everything over x0. So so I have on x0, I consider x0 as a log scheme. Well, the log structure is just the pullback of the log structure on everything given by this divisor. So, but well, this MGR has this very simple description. So these are the constant shifts on d0, on di extended trivially to everything. And I want to, in this case, I want to look at x log and realize it as a element of the A1 homotopy category. Okay. So, well, what you do, is the following. So, well, I need another piece of notation. So let's call Li circ. This will be GM torsor associated to Li. So Li is a line bundle. I take the total space. I remove the zero section. Okay. And then, so what I want to do, I want to consider the following complex. The following complex of, so I want to construct, well, Voevodsky motif, and well, in fact, it will be even element of stable homotopy category, and even unstable after a certain modification. So, okay, so what is this? So let's first define it as a motif. So, well, I want to do something very, very simple. I will take L circ. So again, this is, I regard it as a scheme living over x0. And I want to restrict it to U1. Right. So sorry. I think I want to restrict it to U2, of course, because it's trivial on U1. Yeah. And then the second thing that I want to do, I want to take L circ 2 and restrict it to U1. Okay. So when I write square brackets, it means that I consider this as a motif. Just it's a plain scheme, so it makes sense. Well, and what I will have here is L circ 1 times L circ 2 over x0 restricted to D12. Okay, so and this D12 is the intersection. Okay. So well, so my motif is going to be sort of the cone of this map, this complex. Now I need to tell you what this is, this arrow. So and here is a reminder. So well, this construction is possible because, well, in the category of Voevodsky motifs, you have identification between punctured tubular neighborhood of a smooth manifold with punctured normal bundle. And namely, if you have so smooth y and z, this is closet, smooth, closet, then there is a canonical map in from the motif of the punctured normal bundle to y minus z. This exists in differential geometry. This can be left to Motivic category. Well, the map that I have here is exactly, well, comes from, is precisely that map. So here is the picture. So if I have, let's see how we get it. Okay, so here is my D1, for example, and here I have this line bundle, which is L1 circle, right? So, and here I have, this is D1, 2. So I apply this construction. So I have this line bundle, this GM torsor. It lives over the whole D1, 2. And in this, inside this, the total space of L1, I have L1 minus, I have this fiber over D1, 2. And I apply this construction to Y being this GM torsor over D1 and Z being its fiber over D1, 2. Then you get precisely this first map, and the second map is constructed similarly. So you do this.
And do you put a sign, or it is not important? No.
I don't think that there is any sign here. It must be symmetric at this moment.
No, but if you have several things that intersect each other, and let us say go in a loop.
No. Well, so I don't think that there is any sign in this picture. So maybe in. So let's. It seems to me that. It seems to me that at least here you don't need sign, but maybe or by sign, it's possible. So okay, so in fact this map that I used here exists even in A1 just in A1 homotopy category, but only after suspension. So so you can kind of do the same doing. Except that what you'll get, you cannot get homotopy type of X log itself, but you can get homotopy type of the suspension of X log. So at least you'll get something in the stable homotopy category. So the fact that that map exists after suspension is proven by Morel and Voevodsky. Okay, so and well, one more remark about this whole picture. So in fact, this ALI have additional structure if they come from this semi-stable degeneration. Namely, L1 tensor L2 is trivial. Well, strictly speaking, this trivialization depends on the choice of a parameter here. Well, I choose a t coordinate, right? Because this is OD1 plus OD2, so it's of special fiber. It's lifted from the base. Therefore, if I have a map from this from everything in this picture to this is over x0 to complex numbers, right? So so there is always there is a map from these guys to complex numbers, from invertible complex numbers, right? So and therefore, so let's give a name to this. Let's call it motif of x0 m. So it's motif of this log scheme, just definition. And in fact, in this case, this motif is not is a Motivic sheaf. Motivic sheaf over C star. And its fibers, for example, well, you can take fibers over, so every scheme here is is a scheme over C star. So you can take fibers, you have still this map, you get what's called the limit motif, right? So, and the picture here is, I cannot really draw a picture of this gluing of this X log, but this X log here, it actually, it maps to log space associated to the log point. So it maps to the circle. And I can draw a picture of a fiber of this over a point of the circle. So imagine that, for example, you have the generation of elliptic curve. So, okay, so here is my, so it degenerates into a rational curve with two double points, right? So this is non-singular elliptic curve. And this now it degenerates. So what you do, you sort of remove these 2 points, and then you glue along punctured tubular neighborhoods. And then you get something back, well, homotopy equivalent to the original space. Okay. So I want to kind of extend this construction to all log schemes. And in fact, even if you have, in this semi-stable case, if you have many components and multiple intersection, it becomes really, well, direct generalization is really unpleasant because, well, you can kind of write down a similar complex, but, well, you have to do it, lift it in somehow on DG level, and then the square of the differential will not be 0. It will be the homotopy equivalent to 0. And these homotopies are given by some double normal cone constructions, and so it's going to be completely useless, though possible. You can't really do anything with that. So instead, one should look at the dual thing. One should look at the Motivic homology of this motif. And this has a very simple geometric description. I will show it to you at the end in the case of this semi-stable degeneration, but first I want to formulate the main theorem in a kind of in abstract form. So the main theorem is the following. So, well, I need a bit, first introduce a bit of a certain category. I will call it the category of log motifs, but, well, then you will be able, well, we can forget about this. I mean, so first I introduce a category that I will call the category of log motifs. So, and in order to do this, so let me just write down definition of usual category of Voevodsky motifs, and then I will list 2 more kind of relations and get the category of log motifs. So, well, so I will work with so log motifs. So I will assume for simplicity that characteristic of my base field is 0. Well, if it's p, you can do the same thing, but you have to invert p in the coefficients. And then, okay, so for Voevodsky motifs, you do the following. Motifs. So you consider category of schemes, say of finite type over a field. And then you form an additive category, just objects are schemes, all schemes of finite type, and morphisms are linear combination of maps, no correspondences here. And then I want to take complices, finite complices over this. And then I mod it out by certain relations, by subcategory. So this is a well, if you can do it on triangulated level, pass to homotopy category, then take Verdier quotient, or you can regard it as a differential graded category. So, and what are objects of T? So, objects. Of T. So, well, I will list them. Let me start. Okay, here. First object is, well, it's going to be class of objects, right? So it's X. So objects are complexes of schemes, right? So this is first. This is called A1 homotopy. And then the second class of objects is, well, perhaps I have to, let me do it here. This will, the second class of objects, I will refer to it as CDH topology. So these are generating kind of sequences, covers. So there will be two parts. So first, suppose I have open, Zariski open subset, and I have an étal map. This is étal. So what are the conditions? Condition is that the map P inverse of from x minus u to x minus u, this map P, the restriction, is an isomorphism of schemes. So that means that this is an étal map, and on the complement to u, it has a section. It's actually a bijection, right? So this is Zariski open, this is étal. So in particular, u and w cover x, but it's much more than that. And in this situation, I want relation, and this relation has the form x u w, and here I have the fiber product u w x. Okay. So obvious maps. And so this is part A, and part B. So I want the following. I consider maps P from x prime to x. These are proper. And I assume that there exists a closed subscheme here. Sorry, maybe I should close it subscheme, such that over the complement, this map is an isomorphism. So P induces an isomorphism between P inverse of x minus z and x minus z. Okay. For example, blow up. Okay, and in this situation, I want to have the following relation, that motive of x prime plus motive of z, and this maps to motive of x. And here I have motive of preimage of z.
And here you must put a sign somewhere in those things.
Yeah, I have to put sign. So either doesn't really matter where. So yeah, you're right. So I have to take the difference, otherwise the square will not be 0. So right. Z is closed, right. So, and also A, B, C, D. Okay. C is that the map from X reduced to X is, must be an isomorphism the quotient. That's it.
It follows from B because you can take Z to be the.
Okay. Okay. So, but yeah, you're right. So many things, in fact, follow from others here. So, and well, you can so this is not that's not so you can have. So this is not what's called usually called the category of Voevodsky motifs. It's also defined and studied by Voevodsky, and it has a very complicated notation. This category, this quotient. So let me give it here. So it's H A1 CDH, and then here I take Z of schemes, and I need Karobian completion of this. Okay, so what is the relation of this category with the category of Voevodsky motifs? So there is a well, at least there is a functor. So this Z to Voevodsky category, which is obtained exactly in the same way, except that you add transfers. So you start with consider the same relations, but this category is different. You consider schemes and where maps are finite correspondences.
And also only smooth schemes.
Don't think that if you do CDH topology, it makes any difference.
You're speaking about now the. Okay, so you can do it with.
Yeah.
Okay. If you don't.
So if you consider smooth schemes, then CDH topology, then B can be derived from A and other axioms. Okay. So now I want log motifs. So what I do with log motifs? How I so let's just consider the same similar category, but let's start with log. So by log schemes, so I consider, I mean F as finite saturated log schemes. Okay, and then I want to take I want to consider quotient of Z log scheme by T. Well, and what is what is this T log? Well, so T log consists of it's a full subcategory of objects. Well, I need not be objects of type 1 and 2, and the following. So I need to impose a bit more, a few more relations. So okay, so what are the relations? Well, maybe just before we explain the relation. So what I have here this. Well, there is a homotopy equivalence relation. So in this homotopy equivalence relation, X is allowed to be any log scheme. as well as here. So I want everything in this picture, x, well, this must be log schemes.
What about A1?
A1 here is just usually A1, but I will add axiom for log A1.
And if you speak about close immersion, perhaps you want the exact one.
Yes, yes. So okay, so what I want is the following axiom. So I have A1 log. So what is it? It's a the underlying scheme is A1, and the log structure is given by 1 point. So my M group is just corresponds to the line bundle of this point. And here I have log point. It's kind of the origin. And here I have GM. It has trivial log structure. So, and I want these maps to be isomorphism in my quotient category. But not only this. I want multiply this by x times A1 log. And again, x is any scheme, log scheme. And also this GM times x is embedded here. Okay. Well, there is one additional axiom. It's strange. It just has to do. We already observed that well, all the construction we have made so far depend only on M group, not on M. M is irrelevant, and I could consider the category of log scheme just by the category of extensions.
So what do you say about them?
They are in my category T.
So you require them to be
Zero.
Okay.
After all.
Isomorphic.
Yes.
You wanted that A1 log is isomorphic for you to the
Yes.
A1 log.
Yes. Yeah. So these are objects in T, like for example, as those objects. So and finally, 4 is very strange. Well, so it's very is the following axiom. So suppose I have any map P from x prime to x. These are log schemes, and the underlying map between usual schemes is an isomorphism. And suppose that it induces the map induced on M group P upper star to M prime group is an isomorphism. Then I want the following relation that x prime goes to x must be in my category. So this kind of a way to say that everything depends on the M group. But again, so I can consider just the category of pairs x plus this extension of O star, this O star. So now, very good. So here is the theorem.
Now, when you do log blow-ups, it seems when you do the operation of log blow-up, I think that the space, I don't remember now, the space x log doesn't change? Or
No, it changes.
It
Well, the
changes.
space X log, yeah, it changes, but it's the same homotopy.
So here is the theorem. I have category A1 CDH so this is my category, and here is the name for this. So this is Z of smooth schemes, so there is of course a functor to this larger category. I consider A1 CDH, and here I have Z log okay, so Right. So this functor is an equivalence of categories. So what does it mean? So what are, for example, functors from this category to, say, the category of complices? These are homology theories, right? That satisfy these basic properties. The claim is that any homology theory can be extended uniquely to log schemes, provided it has all these properties. Okay, so so let's see. So in particular, well, of course, here you have map to functor to usual Voevodsky category, and then you can compose the inverse and get Voevodsky motif. Now, so the construction, the proof uses very little geometry. In fact, it's more or less linear algebra, and so well, first of all, no, you have to prove. So you have to prove two things: that this functor that I have here, the obvious functor, let's give a name to this functor. Let's call it phi, is fully faithful, or homotopically fully faithful if it's DG. You think of this as DG functor. So fully faithful, and B, so essentially surjective. Surjective. Well, and in fact, so easy step is that A implies B, and therefore prove. So all you have to do is to prove A. So and that's because and you can do it by induction on dimension. So you need to show that any motif of any log scheme is in the image of this. Of this functor. So you have enough relations to express a motif of any log scheme in terms of motifs of usual schemes. So, but that's easy. So you do it again by dimension of your log scheme. So if it's zero dimensional, then well, it's fine saturated. So it means that my monoid M group is just z to the n, and the corresponding, so if I have point and take its, well, its motif, for example, is motif of GM, and if I consider Cartesian product of any scheme of log point with itself, then it's of course it will be GM times GM. This follows from this axiom. So using this property, any zero-dimensional log scheme has the same motif as product of this. So now what you do in one-dimensional case, so you have some curve. Now generically over an open set, the log structure is trivial. It just corresponds to trivial extension. M group is just trivial extension of z to the n by O star, and therefore okay, so you know what to do over an open set, and then you can use this CDH axiom to see that this log motif of this curve is also in the image. So what? You
haven't used fully faithfulness yet, have you?
No, I used because so let's see. Well, if you look at the CDH axiom, how it looks like. So you have some P inverse of Z, and then you have Z plus X prime. And this maps to X. So I want to show that that this object so that this object, so knowing that this object and this object are in the image, and also this, I want to conclude that this object is in the image. But then I need a map from X, from this square bracket X to this guy. And I need to show that this map exists in the usual category of Voevodsky category. It exists by definition. Because it's an exact triangle, there is a map from square bracket X to this guy shifted by 1. And I need to show that this map actually exists. So, and now, so what you do for...
Do you assume that the log structure is a risky locally trivial?
I use that it's the risky locally trivial, right? So I could, yeah.
So it is, and so you don't have motives for etal.
Then I need to work with etal topology rather than with the risky. Well, at the end, I will get an etal Voevodsky motive. Well, some applications that I had in mind have to do with this integral weight filtration, which exists only for realization of usual Voevodsky motives, not etal. So, okay. So what you do for A? So what we have to, it's enough just by formal nonsense. It's enough to prove the theorem. It's enough to do the following. So given any object of this category, H usual category, A1 CDH. Maybe I will just say the following. So let me, because my time is short, so I claim that it's enough, it suffices. I will sort of suppress the completely formal part, so it only uses the fact that the category of Voevodsky motives is rigid duality. It suffices to show that the functor home Z of n from this usual category of motives CDH Z of schemes extends to larger category, this category, A1 CDH Z log. And what you do here, you just sort of you want kind of to define Motivic homology. It's not quite Motivic. It's home in this category with no transfer. So I don't want to call it Motivic homology. It would be Motivic homology if I consider this category with transfer. So you want to do it for any log scheme, and the idea is very simple. Well, you have the same group. It can be evaluated. It can be considered as a Motivic sheaf over this Motivic sheaf. Sheaf over the underlying scheme. That means simply that you can evaluate it over any scheme which is smooth over this guy. You simply pull the log structure. If I have a map like this, then you can pull the log structure, this log structure here, and take the anchor there. So, and then what you do, you just compute, you take homology of x with coefficients in symmetric powers. These are operations in the category of Motivic shift symmetric powers. Well, they're defined by Voevodsky. They're characterized by the properties that if you take x, that motive of a scheme x is the symmetric power of motive of a scheme x is the motive of the symmetric power of x.
Are you using M bar group or M group?
Just M group. So, for example, what happens if your n is 1?
Well, when you pull it back, you don't make it a log structure on Y. You just take. You don't enlarge the units. Usually when you pull back.
Do you enlarge units?
You are going to enlarge them.
Yes. So, for example, what is first Motivic homology with n equal 1? This is just homology of M group. It's kind of analog of the Picard. So. Okay, and now I want to finish by.
Homology, which category?
This is this is the
Homology in what?
this, well you.
From the big heuristic homology of X.
Yeah, this is Nisnevich homology of this Motivic shift. So, well, I want to finish by a very explicit formula that I promised at the beginning. Just very geometric, for the Motivic homology of the limit motive in the case of semi-stable degeneration, and also for the tubular neighborhood. It will be just in the case of semi-stable degeneration, and it comes from this. This formula is here. I just want to. I will make it explicit, which is trivial from this definition. So the formula is the following. So here is my setting. Well, now I will have, again, I have the log structure coming from semi-stable degeneration, but now I can have multiple intersections. Well, but it's still semi-stable. Maybe that's not a good picture. So this should be planes rather than lines. So, okay, probably I should not put it here. Yeah. So it's confusing. Okay, semi-stable degeneration, and it's strict, right? So I want really I want log structure for the risky topology. So strictly semi-stable degeneration. So I have components d1, d2. Well. So di I belongs to some set. I have this GM torsors. So first of all, I have Li, which is of di restricted to x0, and then I have the corresponding GM torsors, and I have Ui, which is the complement of x0 to di. So okay, so now I will construct the Motivic homology. So, well, first I will produce a complex of smooth varieties over x0. The fibers will be algebraic tori. So what are these varieties? So step one, complex, well, very simple. Complex of smooth varieties. So this will be product of all this Li. So this is product over x0. It's a torsor over an algebraic tori of dimension cardinality. Now, what is the next term? So you take sum. Let's consider it as a kind of. I want to. It's not really. It's in fact it's a. I want to consider kind of an additive category I want to make sense of sum, so it means that it's you can think of this disjoint union, okay? A disjoint union. So of products of I in I is not equal to J. And here I will have L circ I times UI over F0. So what is this map? Remember that Li is trivial over UI. Therefore, I have such a map. It's just given by, well, it's section. Now, it's a long complex, and here is its last term. It's sum I over times intersection J not equal to I, Uj. It's gain over X0. And so all I use here, all the differentials come from the sections. Remember that Li is trivial over Ui. So this gives me such a, again, this should be disjoint union. So this is step one. It's very simple complex. Now form, define a complex of pressures on X0. Well, what you do, so you call this Z dot, and then you take the following. So if you have a scheme over X0, then, well, the value of my complex of pressures on X0 on Y is the following. You take correspondences over X0 from Y to this complex. So, well, informally, you just take sections of this complex of varieties over Y. And then you make it homotopy invariant by applying the Suslin construction. Yeah. So let's call this F, and my Motivic homology of X 0M Z is just CDH homology of this X0 with coefficients in F. That's it. That's all I have to say. So there is one, well, there is, as you see, you can ask whether the log geometry here, and in fact there is no log geometry. You see it's just linear algebra, and the log geometry appears if you want to prove, for example, that if you have a smooth log scheme, then its motive, it's isomorphic to the motive of the open part where the log structure is trivial. This I don't know how to do. I know how to do it in the case of like normal crossing, in the normal crossing situation, but in general it really requires some geometry. Thank you very much.
Was there any cases in the notation of the Motivic homology? Did you say you have several, you have Zn for different n?
Yeah, so here I defined only with one index, right? This index is absolute value of this set of indices, I. So if you want define it for larger, for larger n, right? You have to just add in the whole construction empty divisor formally.
And to define it for smaller, you don't.
Yeah.
You don't.
You don't need to define it for small by cancellation. It suffices to define this for sufficiently large numbers.
This follows from the proofs.
Yes. No, just Motivic homology. Yeah. So if you want it for you have cancellation, so you can express Motivic homology of something with coefficients in Z of n in terms of homology of the twist with coefficients in Z of n plus 1.
Which twist? The product with GM? Or?
Yeah, product of this GM, for example. Yes?
So I just was curious, what is n?
Where is n?
Shouldn't we have if we have Motivic?
Yeah, this twist here, right?
No, n
This
means the log of monotony.
Yeah, it's that's very good question. It's this whole complex of schemes. It's least over GM. If you have this, it's exactly as in the picture I started with. This gives you the tubular neighborhood. If you want really the limit, the vanishing cycles, you have to take the fiber over. So it's unipotent Motivic sheaf over GM.
But how can you define them up to GM if you are given just you're in the fiber?
No, there is a the map to GM comes from the trivialization of the tensor product of these line bundles. So each of this smooth schemes of these schemes over X0 admits a map to GM. For example,
Because the other one,
the product is Mm-hmm.
Well, this is implicit in what you said, that you started talking about how to define the weight filtration.
Yeah.
Does this come out easily from this?
No, Betty. Yes. So there is a yes, it comes thanks to work of Bandarka. So if Betty homology or the RAM homology of Tal homology of any Voevodsky motif is equipped with integral V filtration.
Yes, and after you have to show that is equivalent to...
Rational. Yeah. To what?
Yes, he has defined the weight filtration.
Yes.
But after, you have to show that it's equivalent to the others.
Well, but here you don't have, well, a priori you don't have the others. What you have to show is that the basic homology of this log motif of this Voevodsky motif I defined coincides with homology of this as defined by Kata and Nakayama. But this is obvious because Kata and Nakayama homology theory satisfies the list of my axioms, and therefore this functor from log motifs is uniquely determined by its restriction to usual motifs, and for usual schemes there is nothing to prove.
And sorry, last question. In characteristic P, this was everything characteristic 0. Like.
Yeah, you have to invert P.
And always with Zariski?
Well, yeah, for the Zariski again, so the only reason why I work with Zariski is that I want Voevodsky motif really for Nisnevich topology as opposed to Voevodsky motifs for Tal topology.
so it is enough to have Nisnevich locally, Nisnevich charts for the rock structure.
Yes. Though I don't really know. No, maybe that way. Yeah, there are examples. Yes.
You need that. Yeah, general. It's not trivial.
Any more questions?